I'm going to give a somewhat experimental talk today in that almost a little more than half of it is all just going to be in kind of one small example. So hopefully we'll kind of get to know this example really well. But if you want to see kind of a more traditional, standard, usual version of this talk, I did speak about this work almost a year ago today in the Paris Algebra seminar. And I have notes and like a video on my website. But Google hasn't indexed this yet, so it's very hard to find. You have to like actually have this URL. But OK. The only way the talk's going to go well is if you ask like a bunch of questions. And so oftentimes people have in their mind like, I don't want to derail the talk from what's supposed to happen. But my talk should be thought of as already off the rail. And you can just kind of nudge it back a little bit, maybe just temporarily. And so let's get started. I should explain all the words in the title. And I'll do them in opposite order. So quivers, Dynkin quivers, then preprojective algebras, then multiplicative preprojective algebras. So yeah, let's get started. So a quiver. I'll just denote quivers today by Q. And they'll have a vertex set, Q0, an arrow set. And the thing that makes this, these are just literal sets, the thing that makes it an arrow set and a vertex set is two maps, the source and target maps. Right, that tell you how to glue the arrows to the vertices. If there was just one boundary map here, this would be the data of a graph, but I'm telling you where they start and end, and so this is a directed graph. And the only reason you would call this a quiver is that in mind you're thinking of like representations of this, or you want to define some algebras. And so it's only kind of a small sub-community that would not just call this a directed graph, but that's all a quiver is. And so let's do an example. If you want to give this information to a computer, you'll actually write down kind of sets like this.
What's the difference with a directed graph?
Yeah, so this is, we'll see it in the example in a second. I'm telling you the source and the target, two different, sorry, what's the difference between this and a directed graph? This is a directed graph. Yeah, sorry. It's very goofy, but it's a notion of like terminology with a purpose. If you say quiver instead of directed graph, it means there's a certain kind of mathematical question you're going to care about next, and that's kind of the direction we'll go in. But all I've defined so far is directed graph on the board. OK, good. So let's say the source of A is 1, and then the target is 2, which will be the source of B, and then the target of B will be 3. So anyways, you never write the quiver like this. You always just visually draw it because we're visual creatures, and it has all the same information in the drawing. But anytime I draw a quiver today, I do want to actually label all of the vertices and all the arrows, because that kind of bookkeeping is going to be important for us. So next, we're only going to be in the setting, even though I wrote Dynkin, of ADE Dynkin. So simply laced, and so I'll just say what those are here. So the AN quiver will just be this line. And then from here, I have the colored chalk. I could branch out like in a different direction. And then the white with the yellow will be my kind of dn plus 1. This n denotes the number of vertices I have here. So n plus 1 for that. And these are two infinite families, the D and the E, the A and the D. And then there's 3 more.
Can you just branch off from the n minus 1?
Wait, what?
Can you just branch off the n minus 1?
Yeah, so for the dn, I just need to have the single like valence 3 point.
Okay.
I guess I could have done it there too.
Okay.
Yeah. And the orientation today isn't really going to matter, which is cool. The orientation does matter, but I'll explain what I mean later. We'll define an algebra associated to it that's independent of the orientation. Okay, 1, 2, 3, maybe come down. And then I ran out of room. Okay. Okay, so this has 6 and will be my E6. And then the 7 just extends one further. And the 8 again extends one further. Okay, and I didn't draw these as arrows, even though I was supposed to. Today, it's not on that one, but I'll put all arrows going towards the central vertex. And it's kind of important information that all of these underlying graphs I'm looking at are star-shaped. So they have this one central vertex, and then there are a bunch of kind of arms coming off of it. Okay, so first kind of two things are defined. These are the ADE quivers. And now we need to associate some algebras to these quivers. Okay, so additional piece of information, K, a field. Except K will maybe also be a commutative ring at times. So I'll take it to be the integers later. But that's fine. People usually have field. So this, I'm defining the path algebra. As a vector space, this is k-linear combinations of paths in the quiver. And a path is a composable sequence of arrows. Okay? That's just as a vector space. The multiplication is concatenation. And then at least if Q0, the vertex set, is finite, like it is today, then this will be unital. And the unit is the sum of idempotents at the vertices. So I should explain this. It's a little strange. My vector space is k-linear combinations of paths. I have a path length grading. That's going to include a degree 0 piece where I'm regarding each vertex as itself being a length 0 path. And then these are idempotents. And that if I have two different ones, they multiply to 0. And yeah, otherwise they square themselves. I mentioned the path length decomposition, but also because of these idempotents, there's a decomposition just in terms of starting and ending vertex. So I'm just kind of noting this down here because we'll need to use it a bit later.
So multiplication is concatenation. If they're not concatenatable, it's 0?
Yes, yeah, thank you. So, yeah, or 0 otherwise.
And
Okay.
do you assume Q0 will always be finite?
Yeah, so today, let's just, we'll just take it to be, these quivers, so it's okay. And so our path algebra will be unital today. Yeah, good question. Other questions? Maybe just a quick example of these algebras. So, okay, so this, we already gave this a name. This is the A3 quiver. And then the path algebra is going to be isomorphic to this. I am going to run out of room for the online audience, so I need to see what they can see. The point is the stars are in the field. Maybe the isomorphism is easier if I just write the numbers on the sides and we think about this actual decomposition. So what's a path that goes from 1 to 1? That's my that's this idempotent. Remember, the sum of these idempotents is the identity. So that's what I'm getting along these diagonals. Here's E1, E2, E3. Here's A is this guy going from 1 to 2. A times B is this one going from 1 to 3. But there's no path going from 2 back to 1. So I have a 0 there. So OK, so this is how you go from the quiver world to the algebra world. And these algebras aren't always kind of by themselves kind of sufficiently interesting. So you usually quotient by some relation. And that's what we'll do next. Except we're going to actually double the quivers now. So let's do that. Questions about what's on the board so far? OK. OK, so the doubled quiver, OK, if I have to define it, it has the same vertex set as Q itself, but now I'll have twice as many arrows. And for the first set of arrows, they'll have the same source and target map. They'll be just the same arrows. And for the second set, they're going the other way. And so it's much easier to see in an example than from a definition. If this is my Q, then Q bar, every time I see an arrow forward, I just draw one back. And I'm going to label it like this with a star. And even for a loop, I'll add another one like that. OK. So the path algebra of the doubled quiver is going to be much bigger. Now I have all these loops. And from this, now we're ready for kind of two definitions. The additive, or kind of the usual preprojective algebra, and then the multiplicative. And so it starts, it's going to depend on the field, so I'll put that in 2. You take the path algebra of the double quiver, and you mod out by a single relation that I'll call R-add. That maybe is usually called like the mesh relation or something. It's a sum of these commutators. OK, so just a single relation. Let me, while I'm kind of writing these definitions, get an example going on this board. So back to the small one, this A3. So there's something goofy about writing these commutators here. And what's goofy about it is that each term in the commutator lives in a different piece in this decomposition. And so let's just take the relation R-add and multiply by the idempotents at each vertex, and then see what it looks like. So the only contribution is A goes this way, and then there's an A star I haven't drawn that comes back. And this is 0. For E2, you at least get 2 contributions now, B, B star, and then minus the other way, A star, A. So that's what I meant, kind of the commutator gets separated into different pieces. And then for completeness, the third one is minus B star B. OK, so here's kind of my 3 relations. Let's do the multiplicative one. There's sometimes a parameter that floats around in this definition, but that parameter will be set equal to 1 today. So again, we'll mod by a single relation. That'll be the kind of multiplicative version. Okay, I want this to be equal to 1. Okay, so a couple of things. First of all, from the narrative of the talk, the way this is going to go, the multiplicative preprojective algebra is going to be like the less familiar, newer defined, harder to work with thing, and the additive will be the nice, friendly guy. And so results will be saying things about the multiplicative in terms of the additive. And that's kind of the direction of the narrative of the talk. This was defined in 2006 by Crawley-Boevey and Shaw. Whereas the other one is like 1969 or something, Gelfand, Ponomarev, so much older. When we took this quotient, this was a quadratic relation, and so I still have a path length grading on this quotient. Here, this is not quadratic. And maybe just a quick way you can think about this relation. Take this inverse literally in power series or something, non-commutative power series. So I'm writing this as here. Now, this has a quadratic piece to the relation, which is A star minus A star A. So the multiplicative relation will be the additive one with some higher order terms.
And where would the Q show up if it were to?
Where would, oh yeah, sorry, the Q would be here. Yeah.
Okay.
And so, yeah, the Q would be, you can think of it as like, I shouldn't write it like that because I actually want them to be invertible. Okay, maybe I should write it like this. It's a vector at each vertex. So at every single vertex, I can kind of change this by a different number. And I'm setting it to be a vector that's all ones in the talk. It would be, I mean, if you'd like, there's also a deformed preprojective algebra on this side with a lambda. But yeah, okay. There's two issues with this definition. So one is this element I wrote when I went to expand it out, there's no reason it lives in the path algebra of the double quiver. In general, you'd need to complete it or something. And so you actually need to adjoin it and formally localize. So add in all of these inverses. Okay. For the purpose of today, we won't actually need to add in these inverses. And the reason is that this term is going to be nilpotent. So after some finite stage, it will actually just end. And that will exist kind of in our original path algebra of the double quiver. Second thing I should say about this is that I can't actually just do this where I tell you some product among arrows. We're in a non-commutative world. I need to give you an ordering so you know the order to take the product. And so right after Crawley-Boevey and Shaw defined this kind of in section 1, section 2 is it's independent of the choice of order. So any order you put on the arrows, you'll get an isomorphic algebra. But really, it does depend on that. Okay. Okay, questions? The reason I have this running example is I want to show a feature of the multiplicative relation here. So I just get kind of this contribution. It's 1 plus A star. I don't know, maybe I should write the E1 there, minus E1. And so the relation's not different here at this vertex. Let's go to the second one. Okay, so how do I want to do this? Let me imagine I'm setting this equal to E2 and multiply by the inverse to kind of send it over. And now I subtract over, and it's the same relation as before. So at least in this case, after multiplying by something, I can get the same relation. And then similarly here. I can multiply it over and subtract and recover that minus b star b is equal to 0. So the point of what's on the board in this example is that if you're just in this type A, then there's no difference between these algebras. The ideal generated by the two relations is the same ideal. I didn't do type AN in general here, I just did A3, but the way I was arguing only involved the valence of the vertices. So if it's some valence 1 thing or valence 2 thing, you'll get the exact same relation. So with that, we should turn to kind of the first smallest example where you genuinely have some higher valence. So let's go 1, 2, 3, 4, A, B, C. So okay, this example is going to consume us for like the next 20 minutes. We'll see how much time I have. But
sorry,
yeah.
I think I'm still confused about the relation of our mult.
Yeah.
Where you get the inverse from, or how I should see it in.
So
if you said like for these graphs we started, you don't have to join it.
I was somehow lying about something, but no one else caught it. So you genuinely don't have to join it, but basically the argument is more subtle. What you need to do is define a different algebra where you multiply all the inverses over. In this setting, you can write down an ideal generated by relations that don't have the inverses. That's the setting where this becomes nilpotent. And so instead of first localizing and then taking a quotient, you first quotient, and then the localization after that is the identity map. So if you define the algebra differently than how I did to not involve inverses, you can quotient, not adjoin inverses, and then everything is okay. So, sorry, that was maybe kind of a fast way. This was kind of a subtle point that I kind of intentionally didn't want to have to address. Maybe just in a small example, I should explain this better. So here, what's the point? Here, my longest paths in the preprojective algebra, additive or multiplicative, they agree here, is that I have stuff like AB that goes from 1 to 3, and then I have like an A star A that goes from 2 to 2, and then the third vertex, B star, A star. And then anything longer than this length 2 is genuinely 0. It's in one of the relations. And so at least in this additive side where there are no inverses, when I kill these relations, this term becomes nilpotent. Really, every single path after length 2 is 0. And so at least in this example, you can imagine trying to do kind of this first, and then kind of add in the higher order terms. It's a bit hand wavy, but I can give you kind of the more careful explanation after the talk.
Yeah.
Okay. Are there other questions? So yeah, so we'll ignore the inverses, and I should put a more careful argument at some point about why this is okay.
I didn't really get why they are the same. So like when you multiply, I understand that. So like you are at least doing the same quotienting as in the additive, but it seems stronger.
I only ever multiplied by elements that are going to be
Ah,
invertible.
Yeah.
Yeah, so that was the key point there. Yeah. Okay.
But and what about the e's?
Oh yeah, sorry. The e's should always kind of subtract out if I did everything right here.
Yeah, they do.
Yeah.
Okay.
Okay. This was something that that held like in any setting, so I could put any k here, and these would kind of be equal algebras. In the D4 case, something genuinely interesting is going to happen. Depending on what field I choose, it'll sometimes be the same, and sometimes it won't be. And so that's kind of what I want to explain next. Okay, so the outer vertices that are valence 1 will be the same relation that's just the usual additive one. So how do I write this? Basically, in both cases, A star A, B star B, C star C, these will be 0. Okay, so now what's the central relation in the additive case? It says that any way that I leave and come back, when I sum those, I should get 0. So A star A plus B star B plus C star C equals 0. And these length 2 cycles are going to kind of come up again and again in this analysis, enough where I should give them each a name. And so this one will be alpha, beta, gamma, and the relation says they sum to 0. Okay. The multiplicative relation will be genuinely different. Okay, so the way I'm going to do this is multiply by kind of 1 plus gamma to move that term over. And for these two inverses, I'm just going to compute them. So because A star equals 0, it means that alpha squares to 0. So the inverse here is 1 minus alpha. Okay. Same with 1 minus beta. And now I get the same, moving everything over, I get the same relation as before, alpha plus beta plus gamma, but now I have a minus alpha beta term. So this was kind of as promised, my higher order term, this length 4 path. This is the additive plus something bigger. Okay. Okay, I'll erase kind of these 2 boards. Oh, okay. Oh, I see. Okay.
Did you get these relations from A times A star 0, or you just impose them?
Oh, no, I'll explain them. So they were, the relation I wrote there is the set at the central vertex, E3, but the relation at the first vertex, E1, this is, says A star equals 0. So I'm taking the relation I wrote down and I'm hitting it with that first idempotent. Maybe I'm slow at erasing, so I'll just erase the whole. Does that make sense? You still seem unhappy, but I can...
I only see a relation if you put an E3 before that. That's what you mean.
Oh, yeah, I see. So the 1 here is the sum of all of them.
Right.
And so then when I hit it with the E3, I get an E3 there and like an E3 there. So I get 2 E3s that kind of subtract.
Right. And then you get it's equal to. The only issue with this one that means those upper relations, they just couldn't follow.
So I see, it's those relations, yeah.
Yeah, but is that your starting situation?
Well, the reason I went so fast over it was that this was supposed to tell us in general what's happening in the valence 1 situation, that the additive and multiplicative will both give us the only, leave with the path, come back with the reverse path, and then you're 0.
Yeah.
And so because this relation doesn't care what's happening in other places of the quiver, it was just, this was the calculation we kind of already did 1 to 2 there, and then we have the same kind of arrow A 1 to 3 in this setting, getting the same relation.
Okay.
Yeah. So at least if I did the talk properly, I was supposed to like explain it really well here, and then we would use that explanation there, but maybe it didn't make sense the first time either. But okay, is it slightly better?
Yeah.
Relation. I should probably so the point is you hit this with like E1, and then the only possible path here that survives is the AA star in this case. And so you're getting kind of an E1 plus AA star minus E1. Okay. Okay, so sometimes it's easier when you're thinking about these algebras to just, let's just look at things starting and ending at the central vertex. We have these 3 length 2 paths. And then I'm saying that each of them squares to 0. And the additive relation says that they sum to 0. So this is like an exterior algebra on alpha and beta. I'm using this relation to say don't ever go to vertex 4. So just to get things in terms of alpha and beta. And then they square to 0, and their sum squares to 0. Right, so they anti-commute. Okay. Okay, now I want to explain an argument of Crawley-Boevey student Shaw, and it's kind of amazing what he did or how he thought about this. So the thing he realized about this example is that you get this isomorphism if and only if the characteristic of K is not 2. So in characteristic 2, there's some issue, and otherwise, yeah, you always get it. And his strategy was to correct the isomorphism. He argued if there has to exist one, I'm going to multiply by automorphisms here on the familiar side where I'm more comfortable. And I'm going to continue to strengthen the isomorphism to have better and better properties. And the corrected thing, so if that's phi, then var phi, this should take each vertex and send them to itself. And so it's preserving that decomposition that I wrote down here and then erased. And because it's preserving that, an arrow like A, it can go to kind of some scalar times itself. It can't go to an arrow because it's not in the same decomposition. It can only go to stuff that starts at 1 and ends at 3. And the only other thing is doing A then beta. So if I take this relation and multiply it by A on the left, then I see A beta plus A gamma is the same. And this is the length 3 path. And then when we get longer than that, like longer than alpha times beta, then we're 0. So there's just a length 1 thing and a length 3 thing. And Shaw missed some additional automorphism here where you rescale by the arrows. And then this arrow just goes to itself plus a higher order term. So a general form of what a map has to do after you've corrected is just it's just in terms of this single parameter, CA. And if you do the same thing with A star, you need to choose A and A star so that they actually descend to this multiplicative preprojective algebra. So A star has to be 0 on this side. And it will go to A star, which is 0. But then there will be a higher order term, which is A beta A star. And then kind of longer stuff. Any longer path has to be 0. This is genuinely a non-zero path in this algebra, so I'm imposing a relation on these coefficients that they have to sum to 0. Right? 0 needs to go to 0. That term was 0. Longer stuff was 0. But I need that sum to be 0. OK. And the situation for D4 is completely symmetric. So B goes to itself plus kind of length 3 with a coefficient. B star goes to itself. And then those two coefficients have to sum to 0. OK. So with that in mind, the next thing Shaw asked was, where does alpha go, the A star A? Well, alpha plus CA. How do I want to write this? So alpha goes to itself plus these kind of two longer length 4 terms. But remember, we wrote a relation between these. These sum to 0. And so it goes to itself plus twice C alpha beta. So maybe I skipped a step. It's this minus that, but then they sum to 0, and so you get twice one of them. OK. This is where the 2 is coming up with the characteristic 2. The only corrected map in characteristic 2 sends alpha to itself. And then that's a huge issue when we want to send the whole relation. So this needs to be 0. But we send it over in characteristic 2, and it's just alpha plus beta plus gamma. And then this term doesn't die. So this would go to, yeah, this would just have to go to the same thing. Great, so this is a contradiction, but in his proof, he also just tells you how to find an isomorphism if you can invert 2. And so it's not so bad. Just take A and send it to like A minus 1/2 A beta, and take A star and send it to A star plus 1/2. Something like this. And then every other arrow can go to itself, and every vertex can go to itself. So we have the isomorphism if we can invert 2, and then if we can't, they're genuinely not isomorphic. OK, questions about this?
How do you correct the isomorphism?
Oh, yeah. So he does it in 4 steps. So So the very first thing is that take KQ0 in here, it's separable. It goes to something separable in here, and then it turns out anything separable has to be conjugate to KQ0. So step 1 is apply some conjugation, so KQ0 goes to KQ0. Now idempotents still have to go to idempotents. That's kind of step 2 because of the algebraic property, but you could have some automorphism of them, like a graph automorphism, where I send them around the horn or something, E1 to E2, something like that. And so the next thing you have to argue is that the automorphisms that are graph automorphisms in here extend to an algebra isomorphism. And that's fine because the relations are kind of symmetric in how they sit at the vertices. So everything's OK. That part of the argument was actually kind of my argument refining his. He does like some numerical count to show that the central vertex has to go to itself. But I think the graph automorphism thing is maybe the right way to think about it. Once you have the idempotent EI going to itself, then you're preserving this decomposition of the vertices, and this part kind of becomes automatic. So yeah, that was a good question. And this is, I've never seen anyone write this down in any other context, but it's very powerful if you have kind of these finite dimensional algebras. The thing I'm going to say next is that I write down these isomorphisms in every ADE case. In A, okay, it's easy. But in type E, just to put this into a computer and get it to be reasonable dimensional for how many variables are here, you really need to do this correction, or else it would just be a complete nightmare. So it made it kind of a computationally reasonable problem to approach this correction. Okay, and it seems kind of interesting also in and of itself, kind of theoretically. It's very general as well. Okay, other questions? So from this point, I kind of just made 2 small observations. And so I'll put those on the board. Maybe I'll leave the definitions there. So I'll just erase these 2. Well, okay, we're gonna use this a bunch, so just remember that this one has the AB, and then that one's just the sum. Okay, so the first observation was a constructive observation that when these isomorphisms exist, there's kind of a large class of them, and you can find them or ask a computer to find them. In the case of type D, you actually can just extend Shaw's isomorphism. I was going to write with that. No. Yeah. So even though I said we're going to do this one example for like a very long time, and we will return to it, let's just do D5 so that we can see how to extend it. I'll do a little bait and switch in that I want to think of these betas maybe as being gammas, at least in how I wrote it. But now the isomorphism does exactly what it did before. Yeah, that's the same form, but now has a higher order term in gamma, so gamma squared over 4. And maybe a better way of thinking about what this is that you just have this same expression from before, but now the inverse of this polynomial is just this bigger polynomial because you're not vanishing in gamma squared. And so to get the AA star being 0, here I need this polynomial to kind of be inverse to that one. And it just requires putting in this higher order term that you didn't have to do in the D4 case. And then besides this, the map is basically the same, except you'll just need to do a little correction here too. and then everything else just goes to itself. And so you continue doing this in general, where maybe this polynomial here is kind of q of gamma, and then this is its inverse, and then this one is, I've made a mistake somewhere. Oh yeah, sorry, this is the inverse, but of minus. So anyways, this gives you the prescription of how to do this in general for Dn, and these are kind of explicit isomorphisms that are easy to write down, and you can just do. I wasn't so lucky in type E. I wasn't able to get like nice isomorphisms like this. They're kind of much, much worse. But yeah, so people, there was kind of reason why these should be isomorphic, and there was actually a proof involving DG algebras that these should be isomorphic in type D, but no one had kind of written down an isomorphism, so that was something I wanted to do. In type E, I thought like nothing had been done, and then after I did the work, someone told me that stuff had been done. I felt a little bit dumb about that, but there is some new component. So this board was supposed to be observation 1 of how you can just start building these isomorphisms and just do it kind of step by step as the paths get bigger and bigger. Observation 2 is kind of an explanation of what's happening in terms of these equations, just from a slightly different perspective. And so we define A6, this quotient, where I just take the algebra and I mod out by the linear space spanned by the relations. So, sorry, spanned by these commutators. And so if you haven't seen this before, it's worth noting and also to explain this sick. What is this in the case of just a path algebra? If I have a path P and its source is not equal to its target, then P is itself a commutator. Right, like this. The other term that's P with this on the end, that's 0. Okay. Then if what is this saying? It's saying only cycles survive in this quotient. So the only paths that exist now are cycles, and there's cycles up to reordering or cyclic permutation. Because if Q is A1 times AN, then I consider a commutator like this to be 0, which multiplied this way is Q, and then multiplied the other way sends the A1 to the back. So this 6 space is cycles mod cyclic permutation. And herein lies the kind of key difference between these two algebras. And it's something you visually can see from the relations that I just erased. So remember, this is like the multiplicative relation. And these are all themselves commutators. That probably requires some explanation. But since AA star is 0 in this setting, this alpha, which is A star A, is a commutator of A star and A. This is similarly a commutator, B star with B, and that's a commutator. And so the question remains, is this alpha beta itself a commutator? So in the multiplicative setting, I have this relation which says alpha beta is being set equal to a sum of commutators. Alpha beta is vanishing in the 6 space. In the additive situation, that's not the case. Alpha beta doesn't need to vanish, but twice it actually does. And so this is kind of the invariant that's witnessing that these things are different when they're different. And the thing it's picking up on is kind of exactly the next order term in the relation. So it's something that you can now just see visually. So let me explain this kind of a little bit more, and then how am I doing on time?
Fine. Another 5 minutes, I think.
Okay, that's not as fine as I thought, but okay. So let me put maybe that argument on this board, and then I need to like actually state a theorem or write something down carefully.
We started a little bit later, so.
Okay. Okay. So here's the point. So we're going to compute this over the integers for D4, this 6 space. What do I want to say about it? Okay, so cycles can either be length 0, 2, or 4 in this setting. Everything that's in degree 0 survives and is part of this space. In degree 2, I just said that all of these die. Or for example, in length 4, I have alpha beta. And I have other things like A beta A star that ends up being the same. And basically any length 4 path ends up being the same as this one. So what's the point here? Oh, I did this relation already. The point was that if you take gamma squared at 0, but it's also this, and if I'm allowed to cyclically permute, this is 2 alpha beta. So twice this is genuinely 0, but this relation kind of used up all the relations I have in length 4, and you can show that alpha beta itself is not 0. And then the thing I did was the corresponding calculation for the multiplicative thing. And here you just get everything concentrated in degree 0, and there's no 2 torsion. So now I'll kind of state a main result over on that side of the board. And I'll kind of explain what's going on in general. Okay, here's the point. I don't know why I thought I was going to do all of this. Well, where is this even stated? Okay. Okay. So the following are equivalent. Oh. The following are equivalent. And it's for this pair of the quiver, the AD Dynkin quiver, and then, let's say, a field. So one characteristic of K is not bad. Not bad, sometimes called good. So good for Q. And this is just a special set of bad characteristics. So in AN, there are none of these. For type D, it's just 2, which is kind of I was trying to explain before. For E6 and 7, it's 2 and 3. And then for E8, it's 2, 3, and 5. And from one perspective, this is the torsion that arises in the preprojective algebra. And then in the multiplicative thing, there is no torsion. But if you're saying like not bad for Q, you should probably have like, the more geometric minded would scold me and say that this is torsion in the root system or something, which is maybe kind of the better way to say it, but not how I think about it. So this is the thing that kind of you can just check right away. And then the point is that this is exactly when these two cyclic things agree. And this is the only obstruction. So it's actually when the whole preprojective algebra agrees with the multiplicative one. And then this maybe should have some other names attached to it. This is the only obstruction to building a quasi-isomorphism on the DG level. So there's some DG version of these that I didn't get to in my talk. But basically, If there's an isomorphism in degree 0, which recovers this one, then they actually are quasi-isomorphic. And the only obstruction to that is what's happening here on the level of algebras in just this kind of small quotient. Okay, how am I doing on time now? Maybe I should. Okay, maybe I should stop here then. But yeah, thanks for listening.